Right, so here are the electrostatics questions. I don't know which one should we start with, the first one.
So we can start with the first one.
Okay, so it says a very small graphite coated sphere P. Maybe these are not visible, but on WhatsApp they should be visible. Is rubbed with a cloth. So there's P. They say they rub it with a cloth. It is found that the sphere acquires a charge of plus 5 microcoulomb. And yes, the conversion says that microcoulomb is equal to times 10 to the power negative 6 coulomb. And another one that you can get is nanocoulomb. This one is, as the word nano says, is to the power negative 9 coulomb. So you just remember the nano one, then immediately you see that the micro one should mean negative 6. And these are the two that they'll mostly ask, nothing else but these two. Then 5.1 says calculate the number of electrons removed from sphere P during the charging process. So here's the thing. Okay, is there a question?
Yeah.
Yes.
With those conversion, are there others that
Oh
they
yeah.
could ask?
I mean, they might, because some examiners are just crazy, but the only two really that you have to know are this. Something else you can have is micro. I mean, not micro, milli coulomb, but milli just means times 10 to the negative 3. That's like millimeters or something. Then you can have decicoulomb. It's just the same conversion that we did. Centicoulomb, things like that. Kilocoulomb, which is also impossible to have. So that's why I say for most parts or for all these questions, you're only gonna have nano and micro.
Mhm.
As in this next question, you see you have nano where I'm circling red.
Yeah,
But
yeah, yeah, yeah.
yeah, I've seen quite a few times where they have millicoulomb. So you'll replace milli with times 10 to the negative 3 coulomb. Okay, very good question there. So quick revision. This thing you did in grade 5.1. This question you did in grade 10. It says anything that you might see maybe on your table is basically neutral. When we say it's neutral, that means the number of protons. So in that thing, we have protons which are positively charged, and we have electrons which are negatively charged. When we say it's neutral, that means they balance, they are equal. But when we start to rub it with a cloth or with anything, maybe your hair or a balloon, then the charges start to migrate. So let's say you have something like a ruler and then you rub it with a cloth. These things were initially neutral, both of them. I'll just write 3 for each. They were initially neutral. Oh wait, I think, oh yeah, I am recording. So when they are neutral, it means the number of positive things are equal to the number of negative things. But when you start to interact the two materials, what's going to happen is that some of the electrons are going to run away from this and then they go to the other thing. Some of the electrons are going to run away, they go to the other thing. So at the end of the day, now there's no longer a balance. So when there's no longer a balance, we call it charged. And this one also is charged. And this charged can be two ways. We can have a positive charge or we can have a negative charge. When there's less electrons than is needed, then we have a positive charge. Then you can see that if I cancel the positive and the negative, the positives are overpowering. They are left uncancelled. So that's a positive charge. Same applies to this one. If I cancel the positives and the negatives, you can see the negatives are overwhelming. So we call that a negative charge. So for P, oh, by the way, an electron is a negative charge, and the charge of that electron, this is a value that you should know, but you do get in the information sheet. Charge on electron is equal to negative 1,6 times 10 to the power negative 19 coulombs, because it's a charge, so it's in coulombs. So you can see electrons are negatively charged. So whenever you see a sphere that is positively charged, that means we took out electrons, or we removed electrons for it to be positive. As you see with the cloth, with the ruler, we took electrons out of the ruler, so it ends up being positive. We put those electrons inside the cloth, it ends up being negative. So the more you have electrons, the negative you become. The less you have electrons, the more positive you become. Does that make sense?
Mm.
Yeah, very important that you understand that part. Then let me just read the question here. Now the charged sphere P is suspended from a light inextensible string. This is the string as we see. Another sphere R with a charge of negative 9 microcoulomb. So this means this one has more electrons. On an insulated stand is brought close to sphere P. As a result, sphere P moves to a position where it is now 20 centimeters from sphere R as shown. The system is in equilibrium. Let me have that in red. System is in equilibrium. And the angle between the string and the vertical is 7 degrees, also indicated. The first question is to draw a labeled free body diagram showing all forces acting on sphere P. The next question is to define the Coulomb's law in words. The last question is to find the tension in the string for 5 marks. So let me redraw the question out here in an empty space, then we talk about it. So we have a ceiling, we have sphere P. Let me try to get a line. Okay, then we have sphere R, which is on an insulated stand, and then the distance between these two, 0,20 meters. Wait, is this? Okay, no, it's 20 centimeters.
Yeah, correct.
So when I convert, it's gonna be 0.20, ne?
Yeah.
Yeah, so I have to convert to meters, so that's fine. Then the angle between this and the rope is just gonna be 7 degrees. The charge on this is negative 9 microcoulomb, negative 0,9, I think, negative 0,9 microcoulomb. The charge on this P is positive 0,5 microcoulomb. Then the question is to find the tension and to draw a free body diagram. So for the free body diagram, FBD, just free body diagram, we draw the free body diagram on sphere P. So I'm gonna have that replaced as a dot. Then what are the forces that I'm going to have on this sphere P? What's the first force?
Gravitational force.
Gravitational force. So whenever they talk about free body diagram, just know that gravitational force is the first one. It's the one that you're always gonna have, and it's going straight down. Then the next one is just tension, which is pulling P to this side. So I'm gonna call that tension. What is the other force?
Mm. The one pulling P to R.
The one pulling P to R. Very good. And then Lubabalo, what do we call that force? Or what is that force due to?
First applied on first to a point.
Sorry?
The first for P to R is the first pulling force, like the first applied.
No, it's not applied. Remember, the force applied is physically applied. Like if I actually push this thing. But this force that I'm having here is non-contact. It's not applied on. It's basically non-contact. We call it the electrostatic force. Electrostatic force or Coulomb's law force. I can name it Fe or F R on P. But this is, let me call it Coulomb's law electrostatic force. Coulomb's electrostatic force. So when you do electrostatics, you're actually doing this Coulomb's law electrostatic force. And how we find it, because we have to find it, we use this equation, which is Coulomb's law. It says F net is, no, not F net. It says force of electrostatics is equal to K Q1 Q2 over R squared. Do you remember this one from grade 11?
Yes.
Yeah.
Yes.
Yeah. So now we're gonna substitute Fe is equal to K. The value of K, if you check from the information sheet, it's 9 times 10 to the power 9. That's provided for you. And then Q1 is the charge on, I can call it QP actually, QP and QR instead. Then QP is the charge of sphere P, which is 0.5, and then I replace micro with times 10 to the power negative 6. Then I go to sphere R. This one is negative, but when I substitute, very important, I have to substitute it as positive. We don't need any negatives in this equation. So I'm just going to write it as a positive value, times 10 to the power negative 6 for micro, then all divided by, now I have to convert the distance to meters because I only can have meters in this formula. The distance always in meters. The charges always in coulomb. Okay, then let's solve. Let's see what this is equal to.
1,1 times 10 to the power of negative 1.
1 comma 1 times 10 to the power negative
Or negative 1.
negative 1. Okay.
Yes.
That means your calculator is set to scientific. I think if it's negative 1, we can just write it as a decimal. So,
My
yes.
teacher said you should like put it into the scientific form. Like,
What? It's your teacher.
yeah, like you should like put it into scientific form.
Okay. All right. That's fine. But usually we start to, from my experience, we start to write scientific form when the decimal is like -3 or more. But that's fine. We can leave it that way, or otherwise if you want it in commas, that's just 0.11.
0,101.
1 to 1
0,101.
or 101. So let me just fix that here. So make sure we get the same answer, 0.101. That means this part will be 0.101, and then the unit is Newton. Okay, so now that we have that force, we can solve for the tension. because if the free body diagram is this way, then I can just break the tension into vertical and horizontal components, which means I first draw dotted lines around my tension. This way, I see that the vertical is going to be here, the horizontal is going to be there. Then if I express those things in terms of t, this horizontal is going to be t, is it cosine or sine of 7 degrees?
The what? Vertical.
The horizontal.
The horizontal is is sine.
Sine. So that's components, right? You go and when the angle is here, just draw a little arrow for yourself. That's gonna point to the side that is opposite. Then you know, on the opposite side, I always use sine. So it's gonna be t sine 7 degrees, and then that means the vertical automatically is t cos 7 degrees. Okay, then I go back and say, first I'm going to erase this original t because I now have its components. So I can get rid of that. Now we go back to this fact. The system is in equilibrium. What do you understand about the word equilibrium?
That when you add, like for example, when you add t sine 7 degrees plus fr on p, it gives you zero.
Very
So
good.
needed.
Yeah, so that means we have a force balance. It means all forces in the x are going to equal each other. All forces in the y are going to balance each other. So in other words, this means the sum of the forces, I'll do the x-axis, and yeah, we can also talk about the sum of the forces in the y being 0. Sometimes for you guys, they say F net in x is 0 and F net in y is 0. That's the same thing. But because we have this force in the x, that means we can basically take the x-axis. So now, considering this x-axis, we can say the sum of the forces, so I'll choose the right as positive. That means Fr on P is positive, and T sine 7 degrees is negative, and this added together is equal to 0. So once again, these are these forces in the x direction. So this one is positive, this one going to the opposite side is negative. That's gonna give me 0, or you can simply say Fr on P is balancing T sine 7 degrees. Then if I substitute my Fr on P, which was 0,101, this will be T sine 7 degrees. And dividing both sides by 7 degrees, I get 0,101 over sine 7 degrees. Then let's see what our answer comes out to be. Remember the 0,101, if you want to write it in scientific, it's still this times 10 to the power negative 1. I mean, not 0, comma, this times 1,01, 1,01 times 10 to the power negative 1.
Answer is
Uh, is it gonna be 8,21 times 10 to the power negative 2?
8,21
Yeah,
times 10 to the power
times 10 to the power negative 2.
negative 2. Okay, listen, you also get the same answer. Looking at this, I don't think this is correct because the power should at least be larger than negative 1 for this case because I'm dividing by a small number. Just recalculate it again.
Hey,
Make sure your calculator is on degree mode.
Yeah, okay. So I got 8,29 times 10 to the power negative 1.
All right, yeah, that one seems correct. So I'm gonna have 29
I've
times
got
10 to the power negative 1. Are
I've
you
got a
getting the
zero.
same one, said?
I've got zero comma is but I believe that it's the same thing. I got 0,83.
Yeah,
It's the same.
so 0, 0,8, I'll say 829, then the units is Newton. Okay, if your teacher insists that you write scientific, which for me really I don't write scientific if the power is -1 or -2, and sometimes if it's -3, I only write scientific when it gets to -4. But otherwise, if that's what your teacher wants, then keep doing that. Okay, but if your final exam is marked by someone other than your teacher, this really does confuse people. They might give you a wrong because then in the memo they're not gonna write it this way. Just for heads up. Okay. Then Coulomb's law. I think the only question we didn't answer is what is Coulomb's law in words. Anyone who remembers it?
Let me let me try. Let me
Yes.
the net I forgot it. Never
Okay. Start with the electrostatic force.
the electrostatic force. I don't know it. I forgot it.
Okay. It basically just describes the equation, the electrostatic force. I, I won't say the exact one you'll see in your book, but it's directly proportional to the magnitude
The,
of the product of the magnitude of the charges
yeah,
to the
and
product of the charges. Yes,
inversely proportional to the square distance between
yes,
them.
exactly. And inversely proportional to square of the distance between those charges to the square of the distance between the charges, blah blah blah, as the book says. But the keywords they're looking for is the electrostatic force directly proportional to the product of the charges and inversely proportional to the square of the distance. If you get those correct, then that's 2 marks. Okay, any question on the whole thing?
Nice.
Oh, actually, I didn't.
Yeah, that is it.
Yeah, I didn't solve the very first question. You see, 5.1. 5. Oh, sorry. 5.1 is how many electrons were removed from sphere P. So I explained that uh, electrons can either be added or removed, but the equation for that sometimes they don't really give you in metric, but I hope they do. They can write it this way or they can write it this way. But basically what this equation means is that N is the number of electrons. Let me just write it in words. Number of electrons and then Q, I like to call it the change in charge. I'll explain why. And then E or QE, this is the charge on an electron, which is a constant, the value of which is -1,6 times 10 to the -19 coulombs. So to solve that question, 5.1, I'm just gonna say, okay, the change in charge on sphere P, they first told me that it was neutral. So if I write this equation, at the end of the day, I have plus 0,5 microcoulomb, but I started with 0. If it's neutral, then it's 0. So I'm just gonna write the charge for neutral is 0. Then it means the change in charge is basically Sometimes you won't start with 0. That's why I want you to understand this equation. Okay, then when I substitute, the number of electrons is going to be, let's see what we get from our calculators.
3,13 times 10 to the power of
3,13 times 10 to the power
12.
12. Okay, then what would you say the units is?
Is it Coulomb
Coulombs? No.
times?
Remember what we said about the equation. What is n stand what does n stand for, what does q stand for, and what does e stand for? So we're solving for n.
M stands for the number.
Yeah, so that's basically electrons. The units is just electrons. So
Right.
that means this number of electrons were removed from p. So I can say where, actually I get a negative when I do this, and the reason why is when you get a negative with this equation, that means electrons were removed. So at the end of the day, I'm going to write this as a positive number and say 3,13 times 10 to the power 12 electrons were removed, because electrons are basically a count like people. You can't have negative people. But if you say negative 5 people, you might mean 5 people left or 5 people died. So, but at the end of the day, you can't say negative. So 3,13 times 10 to the power 12 electrons were removed from P.
So,
Yes.
seems like we were calculating the value for Q, the change in charge is positive. Can we not, can we just like automatically assume that the constant value for electron, its charge of an electron is gonna be positive?
Okay, yeah, you can use it as a positive, but as long as you know what you're doing, because actually the number itself is negative because electrons are negatively charged. But yeah, you are more than welcome to use it as positive. In fact, sometimes in your information sheet they just leave it as negative. So for this, basically the negative doesn't really matter. It's just there as long as your final answer is positive all the time.
So,
All right. Okay. Very good question there. Question 7 was, okay, let me see, question 9 and 10. I'm just gonna see if there's any similarities here. Okay, I want to, let me read this question. Question 7, the one I have here, says two identical spherical balls P and Q of mass 100 grams. So you see they give you mass here, 100 grams each, um, are suspended at the same point from the ceiling by means of an identical light inextensible insulating string. Each ball carries a charge of, so you're just gonna write this information for yourself, 250 nanocoulomb for both of them, nanocoulomb. The balls come to rest in the position shown in the diagram, so that's basically at 20 degrees for each. Then the first question is to, the angles between each string and verticals are the same. Give a reason why the angles should be the same. Why would the angles be the same? 20 degrees each.
because they just
so is it because the charges are like positive? they're gonna like repel each other.
Yeah, that's one reason, but I think that won't earn you the mark. That's true, but that's not specifically why the angles are going to be the same. So
because
add to that.
yeah,
Yes.
because they are identical.
Yeah, that's because they're identical, or that's because they have the exact same charge. You see, if the charge was different, let me give you an example. If the charge on P was like 100 nanocoulomb and the charge on Q was like 250 nanocoulomb, then you'll see P was going to be pushed far away from Q. So let's say 40 degrees and this one 20 degrees, because this one has a bigger force, or not a bigger force but bigger strength than this one, so it's going to push it away too much. So the reason why they have the same angle is because they are the same magnitude. So once again, the 1 coulomb's law in words, and then they say the free body diagram not drawn to scale of the forces on P is shown. So this is the one you have here. So this force that is going down will be your Fg, and this force here will basically be your Fe, or electrostatic force. And looking at this is P, so this I can write this as Fq on P. Then question 7.3.1 says calculate the tension. You see, to find the tension, because I'm given the um, Fg, you see I have the Fg, which is just mg, and my mass I have to convert that to kilograms, so that's 0.1 kilograms times 9.8. So the final answer is basically 0.98 newtons. I can use that to find the tension, because I know that the angle that tension makes with the horizontal is 20 degrees. Then by alternating angles, I can also say this is 20 degrees. Then I can find this adjacent side as t cos 20 degrees. Then because this is basically in equilibrium, even though they didn't mention, but I think they did mention, it's just different wording. So I'm going to do the sum of the forces in the y equal to 0. Then that means Fg balances with t cos 20 degrees. Can you see? We go back to exactly what we did before. Then my t is 0.98 over cos 20 degrees. Then you'll find your magnitude. Then the next thing is to find the distance between ball P and Q. That's also fairly simple. Okay, let's find this magnitude first. If you have a question, do stop me and ask. I get 1,04 times 10 to the power. No. Okay, Lubabalo, what do you get when you solve this particular expression here? I want to check
Uh,
something.
I got I got 1,04 times 10 to the power
To the power
of
Zero.
0.
0. Yeah. So you see, that's dangerous there, because someone who's marking might mark that as wrong, but uh, loss of exponent says times 10 to the power 0 is basically times 1, so we don't really need times 10 to the power 0. That's why I say we only use scientific notations only when it's necessary. Okay, so that's the answer that we get without scientific. um 7.3.1, I mean 7.3.2, they want the distance between the balls, so that's r between them. Then what do? Let's hear from you. What's the plan? How can we find that distance?
We're going to find a T T sign T sign 21st.
Yeah, very, very, very good. Very good. So we have to find this other side. Then what are we going to use that for?
Then we're gonna equate the FE to sign T sign 20.
Mm-hmm. And
Then
then
we solve.
yeah, that's basically, you see, in physics you just solve things with your head even before you write them down. So I'm going to do the sum of the forces in the x equal to 0. Then that means Fe is going to be equal to T sine 20 degrees. Then that means I can substitute this answer, sine 20 degrees. Then my Fe is, let's see, answer times sine 20 degrees is going to be 0 comma 357. I'll keep it uh, 3 decimal places. This is in Newton. Now look what I have. I have the electrostatic force between these two objects. So I can basically say Fe by Coulomb's law is K QQ and QP over the distance between Q and P squared. So if I substitute 0,357 equals to K is 9 times 10 to the power 9. Um, the magnitudes are the same, so why don't I just say 2 times 250? It's nano, so times 10 to the power negative 9, all divided by the distance between them is what we're looking for. So I'll just write it as R. Then solving this, I'm just gonna cross
Wait,
multiply. Yes.
doesn't two times means that you're adding identical things.
Yeah, exactly.
So
As you're saying it, I see.
you
Yeah,
have to say,
very nice. Yeah, that's, you're focusing. So that's gonna be squared instead, ne?
yeah.
Very good. Okay, thank you. So now I can just cross multiply. 9 times 10 to the power 9 times 250 times 10 to the power negative 9, and I can just multiply twice than writing squared to avoid mistakes, but it's the same thing, over 0,357. Then I remember to take a square root at the end. Then my final answer is going to be, you'll tell me if this is what you get. I'll write this as 3,97 centimeters. But if they specify that, the answer you'll get is basically 0,0397 meters. But if you really want to show, if you want to show off, you can write it as centimeters. Okay, let me see if they specified the units. They didn't, so you can leave this as meters like this. Any question on that? Oh, by the way, you usually use 2 decimal places, so why don't I write this as 2 decimal places, which means it's gonna be 40 meters like this.
Mm.
Actually, that's not even 2 decimal places, but that's fine. Okay, but that's how you'd solve that question. So the thing that you needed to do here is to, which they did for you, the free body diagram on sphere P or Q, because they're identical, it doesn't really matter. And after that, you can see that you have to, oops, I shouldn't erase everything. You have to do the components of the tension as we did it with the first question. So you're gonna have Ty, which will be cos of this angle 20 degrees. And you're going to have tx, which would be sine of this angle 20 degrees. Then you balance your y's and your x's. Then you can solve for the unknown that way. Okay. Basically the same kind of idea with question 9 here. This time I see they give you a sphere that is directly below the other one. So what I see is the free body diagram. Even before I look at the question, we're gonna have tension. I draw the free body diagram for this one right here. I'm gonna have tension pulling it up. I'm gonna have, okay, let me actually get this from you. What are the forces I'm going to have on this sphere? Q1.
Sure. Q1. Okay,
Yeah,
we're gonna have tension,
I'm gonna have tension going up there.
FG going
You
down,
understand?
FG,
FG
FG
is
going down.
FE going down.
FE going down. Good. So that's how your free body diagram looks like now. Um, then you see its equilibrium. Then you're gonna do the sum of the forces and the y is 0. You solve for the unknown.
Mm.
Yeah, simple. Even if I don't do the question, that's how it's gonna look like. Then let's look at this one, electric field. I want to quickly revise with you electric field. And let's look at question 4. Two identical neutral spheres, M and N. If it's neutral, it means the charge is 0 coulomb, are placed on insulating stands. Usually they do tell you insulating. Sometimes they'll ask you why insulating stands. Why would you say? Why should we put them on insulating stands?
to not add extra touches like because of conductor.
Sorry, say that again.
To act as a conductor. The cells act as a conductor to not add extra touches.
Oh yeah. So we basically from prevent charge, and charge is basically electrons, so you can say electrons or charge. Electrons are the things that carry charge, so to prevent electrons from escaping or coming into the system, if I want to have electrons inside this globe, I can't have them running away to the ground, or I can't have the ground taking the charge into the globe. So that's basically why we have insulator there. Then the question continues to say they are brought into contact. Yeah, here's another interesting thing. When we put things into contact, so contact, what's going to happen is they're going to share charge. And remember, charge is electrons. And this sharing is going to be equally. So we're going to need to find the new charge after they separate. So Q new will basically be charge of 1 that we started with plus charge of 2 over 2. I'm sure you remember this one from grade 10. If it's 3 charges, then we're going to add Q3 and divide this by 3. But that's basically how you find the new charge when two spheres contact. Here they say when the spheres are separated, it is found that 5 times 10 to the power 6 electrons were transferred from M to N. So you see what happens now. They tell us that electrons, remember M was neutral, so they balanced, but now there's extra electrons in N and there's less electrons in M. So now we have a charge. So what can we say? What is the charge of M now? Is it positive or negative?
It's positive.
It's positive because we are taking out the negative stuff. Then the charge of N is going to be negative because we are putting in negative stuff, which are electrons. So 4.1 says, what is the net charge on sphere n after separation. Remember, we do this because time is running out now. We do this n equals to q over e, but q is your net charge. So because we started with neutral, that's gonna be just q final minus 0, so we can just leave it as q. So the number of electrons transferred around, actually, why don't I make q the subject of the equation? That means I have n times e, so my n is negative 0.6 times 10 to the power negative 19. This one is a constant, it's given, but that's the e, by the way, sorry. So the n is 5 times 10 to the power 6, and multiplying that, you can see that this is for n. We get a negative answer because n is negatively charged, so we get a negative, let's see, negative 1,6 times 10 to the negative 19 times 5 times 10 to 6, negative 8 times 10 to the power negative 13 coulombs. So you see now the scientific, it's needed, because otherwise you're gonna have 0,13 zeros and then you're gonna have 8 at the end, so you can't write that. This is recorded, by the way, if you want to review it again. 4.2 says write down the net charge on sphere M after separation. This is basically the same thing. You see, they say write down because they know you already have the answer. What is the answer for 4.2?
Is it
Charge on M. Think about it.
it's negative 8 times 10?
Okay, this time is going to be positive. Why? Because electrons are being lost from M. Can you see that?
Uh,
Yeah. So you get your 2 marks for this. You get 3 marks for this one. Then you continue on to electric field, which is the only thing we haven't talked about. So I want to quickly talk about electric field. Then I guess by that we can close off electrostatics. But you get something like this sometimes, which is just simple. If you remember, you did this in a lot in grade 11. They will say focus on this charge B and then write the, let's say it's negatively charged, this one is positive, this one is negative. Then they say write the what is this, the net electrostatic force acting on B. Then you're gonna draw your force diagram. A, since it's unlike charges, it's gonna attract. C is gonna push B away, so that's how your vector diagram is gonna look like, and then your resultant will look like that. And how we find these forces, it's force A on B by Coulomb's law, QA QB over the distance between A and B squared. How we find this one, also Coulomb's law, FC on B is equal to KQC QB over the distance between C and B squared. Then from there, after you find these two sides, obviously you're gonna find the resultant by using which theorem? By Pythagoras. Do you remember this stuff?
I remember the pattern.
Yeah, I'll give you questions to practice that, probably as homework. But yeah, that's that. Before we close off, oh wait, do we have any question? on what we did today, I can go back to a certain question that you want to ask about. Just check and tell me if you have any question, anything that I should repeat. Nix,
So,
yeah,
so I have a question. The reason why I sent question 4 was I couldn't like calculate 4.4 because
4.4.
it is missing values.
Or 4.4, you mean this
Wait,
one?
wait,
This one.
please help me like on 4.4. Can we calculate 4.4? Yeah, can you calculate the value for P by using the distance of 15 centimeters plus 10 centimeters? And then, like, can you do that? Because
Yeah.
the missing value is for P.
Oh, okay. Okay. Yeah. Actually, I want to talk about that quickly, very quick. I did teach the grade 11th this. So I'm just gonna go to the grade 11 chapter here. Let me do this quick. Electrostatics was there. No. Where did I talk about this? Give me a second. Okay, it should be here. Yeah. So if I go back to electric field, let's quickly revise what electric field says. This is electric field. The definition, which they will definitely ask in the test, it says electric field is a region in space where a charged particle will experience a force. And which force are we talking about? The electrostatic force. But in electric field, look at what I do here. I start with electrostatic force, which is the equation you see here. Then I change this other charge, which I'm focusing on. You see the one I'm circling here with the green, with the yellow highlighter. I call that a positive test charge. Positive test charge. Because I'm not really interested in the magnitude of that charge. I'm interested in this. If I put a charge Q, which has a charge and it's going to have some strength, which is called electric field strength. If I put something somewhere in that field, how much force will it experience? That electric field. So I'm not interested in the amount of charge of this test charge. I'm only interested in the amount of charge of this one and the distance between the two. So what end up happening is that I disregard the magnitude of that charge. In other words, I divide by it. So if I divide by that small q, it's going to cancel this side. Then I'm left with this equation. E is equal to F, which is the Coulomb's law force, over Q. But this one you don't usually use. You use this one on the other side. So you can say electric field, which is given by big letter E, is equal to K, which is the constant you've been using, Q, which is the charge that you are focused on, over R squared, which is the distance between that charge and the test charge. And this test charge, we always take it as positive. Then the unit for this is Newton per Coulomb, because we are dividing a force by a charge, and force is in Newton, charge is in Coulomb. But once again, the equation you'll mostly use is this one. So you might want to take a screenshot just so that you remember, but this is also given in the formula sheet. And then very quick, let me talk about electric field lines. You also did this in grade 11. When it's positive, the field lines are going outwards. When it's negative, the field lines are going inwards. And you should have the field lines going perpendicularly to the surface. You can't have something like this. You see, It should go perpendicular to the surface. Then there should be a difference between a larger charge and a smaller charge. Smaller charges have fewer field lines, larger charges have more field lines. Then we also have interaction. When we have unlike charges, we know it's going to be attraction. So positive attract negative. Keeping in mind that negative goes inwards, positive goes outwards. When it's repulsion, like charges, negative and negative, keep in mind they go inwards for negatives, but you should see that they are repelling, they are not coming together here. Okay, is that good?
Yes, that's good. Yes.
All right. Okay, going back to that question very quick. Um, I see time is out here, but I'll just be very quick. This P is actually your test charge, so you don't need the magnitude. Test charge. You don't need the magnitude of P. In other words, you know the magnitude of M though, that's positive 8 times 10 to the power negative 13 coulombs. You know the magnitude of N is negative 8 times 10 to the power negative 13 coulombs. Then electric field is going to look like this. E N on P. I'll just call it En because you know P is not really anything, it's just the test charge. So KQ, this Q is going to be of N over R between P and N squared. So that's 9 times 10 to the power negative, positive 9 into 8 times 10 to the power negative 13. The distance between P and N is 10. So I divided by 100 to get that in meters, then to the power 2. And then you're going to need to also find EM, which is EM to P. So I'm going to have KQM over R from P to M squared. So you can see the equation only requires one Q, which is the Q of M on that side and the Q of M on that other side. So 9 times 10 to the power negative 9 into 8 times 10 to the power negative 13, all divided by, now the distance from M to P is 15 plus 10, right? So it's 25. Okay, so yes, 0.25 all squared. And because P is a positive test charge, here's how your vector diagram is going to look like. N is positive, so I'm gonna do P here. N is positive, so it's repelling P, so that's En. M is negative, so it's attracting P, EM. So at the end of the day, E net is given by En minus EM. Then you're gonna get, um, when you solve this question, when you solve this answers here, I'm just gonna call this, yeah, I'm just gonna leave it here. You're gonna get your answer and then you write your direction to the right. Does it make sense?
Yes, it does make sense.
Yeah. So basically, don't need the magnitude, and other than because we are not finding the Coulomb's law force, we are finding the the electric field. Okay. Yeah. If there's no other question, we can call it a day. I'll send everything on Google Classroom.
Yeah, that's fine.
All right.